The morning of October 1st, 1940, broke clear over Stratford, Connecticut. Inside the Fort Sikorsky aircraft plant, test pilot Lyman Bullard climbed into the cockpit of an aircraft that would redefine what American aviation was capable of achieving. The prototype XF-4U-1 sat on the tarmac, its distinctive inverted gull wings catching the early light, the massive 13-foot propeller dominating the aircraft's profile like nothing ever fitted to a fighter before. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Bullard advanced the throttle. The Pratt & Whitney R-2800 double Wasp engine roared to life with a sound unlike any radial engine that had come before it. 18 cylinders arranged in 2 rows, 2,800 cubic inches of displacement, 1,850 horsepower on tap. The prototype accelerated down the runway and lifted into the Connecticut sky. What happened next would send shockwaves through military aviation circles worldwide. On a flight from Stratford to Hartford, the XF-4U-1 averaged 405 miles per hour in level flight. The Corsair had just become the first single-engine American fighter to break the 400-mile-per-hour barrier. No elegant racing seaplane built for speed records. No stripped-down experimental machine. This was a combat aircraft, designed to carry guns and ammunition, armor and fuel, everything necessary for sustained warfare. And it had just shattered what most engineers considered the practical limit for piston-engine fighters. The speed itself was remarkable enough, but the engine that made it possible represented something far more significant. The R-2800 double Wasp was about to become the most important aircraft engine America would produce during the Second World War. And when Japanese engineers eventually captured and examined aircraft powered by this massive radial, what they discovered would reveal the true scale of the industrial chasm separating the two nations. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of the Corsair begins not in 1940, but 2 years earlier, when the United States Navy Bureau of Aeronautics issued a request for proposals that would change American naval aviation forever. The date was February 1st, 1938. The requirement seemed simple on paper but demanded revolutionary engineering. The Navy wanted a single-seat carrier fighter capable of maximum obtainable speed with a stalling speed no higher than 70 miles per hour. That phrase, maximum obtainable speed, set this competition apart from previous fighter procurements. The Navy wasn't asking for incremental improvements over existing designs. They wanted the absolute fastest fighter that contemporary technology could produce. Everything else, within reason, was negotiable. Range, armament, even some handling characteristics could be compromised if necessary to achieve blistering speed. Vought Aircraft Corporation responded with a proposal that took the Navy's requirement literally. Chief Engineer Rex Beisel assembled a design team that included project engineer Frank Albright, aerodynamics specialist Paul Baker, and propulsion engineer James Shoemaker. Their mission was clear: build the absolute fastest airframe around the absolute most powerful engine available. And in 1938, the most powerful engine available was still on the drawing boards. Pratt & Whitney was developing an entirely new class of aircraft power plant. The R-2800 double Wasp would be America's first production 18-cylinder radial engine. Previous large radials had used 9 or 14 cylinders. Pratt & Whitney was essentially stacking 2 9-cylinder engines one behind the other, creating a massive power plant that promised unprecedented output. The engineering challenges were enormous. Heat dissipation became a critical problem. 18 cylinders firing in sequence generated tremendous thermal energy, concentrated in a relatively compact space. Traditional cast or forged cooling fins wouldn't suffice. Pratt & Whitney engineers had to machine cooling fins directly from solid metal cylinder head forgings, cutting hundreds of thin, closely spaced fins with gang milling saws that automatically adjusted cutting depth to follow the contour of each cylinder head. The manufacturing precision required was extraordinary. Every cylinder had to be machined to tolerances measured in thousandths of an inch. Crankshafts, connecting rods, pistons, valve assemblies, all demanded manufacturing capabilities that pushed American industry to its limits. But Pratt & Whitney succeeded. When the R-2800 first ran in 1937, it produced 1,850 horsepower, more than any aircraft engine then in production. Rex Beisel's team at Vought designed their fighter around this monster engine before the engine itself had proven reliable. It was an enormous gamble. If the R-2800 failed to deliver its promised performance, the entire fighter program would collapse. But Beisel believed the gamble was necessary. To achieve the maximum speed the Navy demanded, they needed maximum power. Nothing less would suffice. The engine's enormous size created immediate design challenges. That 2,800 cubic inch displacement required a correspondingly large propeller to efficiently convert horsepower into thrust. Beisel's team specified a Hamilton standard hydromatic propeller with solid aluminum blades spanning 13 feet 4 inches. It was the largest propeller ever fitted to a fighter aircraft. Now the problems compounded. A 13-foot propeller needed substantial ground clearance, especially for carrier operations where landing approaches came in at steep angles. But tall, straight wings to lift the propeller clear of the ground would mean long, heavy landing gear that would be structurally weak and difficult to retract into the wings. Beisel's solution became the Corsairs' most recognizable feature, the inverted gull wing. By angling the wings sharply downward from the fuselage root before leveling out toward the tips, Beisel created enough propeller clearance while allowing the landing gear to mount at the wing's lowest point. The gear could be shorter, stronger, and more compact. It could retract rearward into the wing without complex mechanisms. The solution was elegant, distinctive, and effective, but it created another problem that would haunt the Corsair throughout its development. The Navy wanted heavy armament. Early specifications called for 230 caliber machine guns mounted in the engine cowling and 250 caliber guns in the wings. Combat reports from Europe in 1939 and 1940 made clear that wasn't enough. The Navy demanded 6 50 caliber machine guns, all wing-mounted. Mounting 3 guns in each outer wing panel displaced fuel tanks that had been installed in the wing leading edges. To maintain adequate range, Beisel had to install an 897-litre fuselage fuel tank between the cockpit and the engine. But here's where the design compromises became critical. To maintain the Corsair's narrow, streamlined fuselage profile for maximum speed, Beisel couldn't stack the cockpit on top of this fuel tank. Instead, he moved the cockpit nearly 3 feet rearward. The consequence was immediate and severe. From the pilot's seat, the long nose and the wing completely blocked forward visibility during the most critical phases of flight, takeoff, and landing. On a carrier deck, where pilots needed clear sight lines to judge their approach, maintain proper angle, and catch the arresting wire, this was potentially catastrophic. Navy pilots who first flew the Corsair recognized the problem immediately. By June 1938, the Navy had awarded Vought a contract to build and test one prototype, designated XF4U-1. This aircraft would prove whether Beisel's bold design decisions would translate into the performance the Navy demanded. Construction proceeded through 1939 and into 1940. Engineers encountered the usual problems that plague prototype development. Systems needed refinement. Manufacturing techniques required adjustment. Components failed and were redesigned. On May 29, 1940, Lyman Bullard, Vaught's chief test pilot, flew the XF4U-1 for the first time. The aircraft performed well, but elevator trim tabs failed due to flutter during the flight. Engineers returned to their drawing boards, analyzing the failure, designing stronger components. More test flights followed through the summer. Each flight revealed new issues and validated design choices. The October 1st flight that broke the 400-mile-per-hour barrier confirmed what Beisel's team believed. They had created the fastest fighter in the world, but more flight testing revealed problems that would delay the aircraft's entry into service and nearly derail the entire program. During full-power dive tests, pilots pushed the XF-4U-1 to speeds approaching 550 miles per hour. The aircraft survived, barely. Control surfaces suffered damage. Access panels were torn loose by aerodynamic forces. In one test, the engine failed catastrophically. Spin recovery proved even more troubling. Navy requirements mandated that fighters recover from a two-turn spin using standard control inputs. The Corsair couldn't do it. Pilots had to deploy an anti-spin parachute to recover safely. The Navy reluctantly agreed to relax spin recovery standards for the Corsair, but the compromise highlighted the aircraft's demanding flight characteristics. As Vought worked to refine the design, events in Europe and Asia made clear that war was coming, and America needed new fighters desperately. On June 30, 1941, despite the XF-4U-1's known problems, the Navy awarded Vought a contract for 584 production F-4U-1 Corsairs. The name Corsair came from Vaught's late 1920s O-2U naval biplane Scout, a tradition the company maintained for its new fighter. Production aircraft incorporated numerous changes from the prototype. The engine was the improved R-2800, producing 2,000 horsepower. The armament was the 650 caliber machine gun installation the Navy demanded. The cockpit received a framed birdcage canopy that provided some rearward visibility through small panels, but did nothing to solve the forward visibility problem during landing approaches. The first production F-4U-1 performed its maiden flight on June 24, 1942. By then, America had been at war for more than 6 months. The Navy desperately needed every fighter it could get. Pearl Harbor, the fall of the Philippines, the desperate fighting in the Coral Sea and at Midway, all demonstrated that American carrier air power would decide the Pacific War's outcome. But the Corsair still wasn't ready for carrier operations. The visibility problems remained. The aircraft's handling during slow-speed approaches was treacherous. The enormous torque from that massive R-2800 engine made the aircraft viciously difficult for inexperienced pilots, especially during critical moments like bolters, when pilots had to execute a go-around after missing the carrier deck's arresting wires. Navy pilots testing the Corsair gave it ominous nicknames: the Hog, for its ungainly ground handling; Hose Nose, for the long engine cowling that blocked forward visibility; and most damning, the Bent-wing Widowmaker, for the inverted gull wings and the aircraft's tendency to kill inexperienced pilots. Yet carrier qualification trials aboard training carrier USS Wolverine and escort carriers USS Core and USS Charger in late 1942 found that experienced pilots considered the Corsair an excellent carrier type and anti-carrier type, very easy to land aboard. The contradiction was revealing. In skilled hands, the Corsair was manageable, even excellent. But skilled hands were exactly what the Navy lacked in sufficient numbers in 1942. Training new pilots to proficiency took time. The Navy needed fighters that average pilots could operate safely immediately. Fortunately for Vought, the Navy had an alternative that met that requirement. Grumman Aircraft had developed the F-6F Hellcat, a carrier fighter that prioritized pilot-friendly handling characteristics over absolute performance. The Hellcat was about 15 miles per hour slower than the Corsair at maximum speed, but it was stable, forgiving, and easy to land on carrier decks. For Navy carrier operations, the Hellcat was clearly the better choice. But the United States Marine Corps operated primarily from land bases, where the Corsair's landing characteristics were far less critical. Marine squadrons eagerly accepted Corsairs that the Navy diverted from carrier service. They recognized that the performance advantages, that extraordinary speed, the powerful engine, the heavy armament, outweighed the handling difficulties on land operations. By the end of 1942, the Navy owned 178 F-4U-1 Corsairs. Early in 1943, the Navy made its decision official. All Corsairs would go to land-based Marine squadrons. Navy carrier units would receive Hellcats. The bent-wing bird had found its home, and the Marines would make it legendary. Marine Fighter Squadron VMF 124 arrived at Henderson Field on Guadalcanal in February 1943, equipped with brand new F4U-1 Corsairs. Henderson Field, captured from the Japanese 6 months earlier, had become the critical American air base in the Solomon Islands. From Henderson, Marine pilots could reach Japanese bases and shipping throughout the region. Control of Henderson Field meant control of the Solomons. On February 12, 1943, Corsair pilots from VMF 124 escorted a Navy PBY Catalina flying boat on a rescue mission. It was the squadron's first operational flight, a relatively routine patrol. 2 days later, everything changed. On February 14th, approximately 50 Japanese Zero fighters attacked the Corsair formation. The engagement became known as the St. Valentine's Day Massacre, though not for the reasons Japanese pilots expected. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The Americans lost aircraft. 8 planes were shot down or damaged in the fierce fighting. But the Marine pilots learned critical lessons about their new fighters' capabilities. First Lieutenant Kenneth Walsh, a former enlisted pilot flying with VMF 124, documented his assessment after the battle. The F4U could outperform the Zero in every aspect except slow speed maneuverability and slow speed rate of climb, Walsh wrote. The implications were profound. If American pilots refused to fight the Zero at slow speeds, if they used the Corsair's superior speed and power to dictate engagement terms, they could dominate. It would take time to develop proper tactics. Marines would die while the tactics were refined. But eventually, Walsh believed, the Corsair would reduce the Zero to little more than a victim. The key was altitude. Walsh learned quickly that whoever held altitude dictated the battle's terms. A Corsair pilot with altitude advantage could dive on Zero formations at speeds the Japanese fighters couldn't match. The Corsair could absorb the G-forces of high-speed pullouts that would tear a Zero apart. The Corsair pilot could climb back altitude using power the Zero's engine couldn't produce, and the Zero pilot could do absolutely nothing to change that dynamic. The R-2800 engine made it all possible. That 2,000 horsepower, delivered reliably hour after hour, gave Corsair pilots options Zero pilots simply didn't have. The Nakajima Sakai engine powering the Zero produced roughly 1,130 horsepower. The disparity wasn't just quantitative, it was qualitative, fundamental, decisive. As winter turned to spring in 1943, more Marine squadrons transitioned to Corsairs. VMF 214 arrived in the combat zone, initially equipped with F4F Wildcats but scheduled to re-equip with Corsairs after their first combat tour. Navy Fighter Squadron VF-17, the Jolly Rogers, arrived in the Solomons equipped with Corsairs despite being a Navy unit, operating from land bases rather than carriers. The pilots learned that the Corsairs' speed advantage wasn't just about catching enemy aircraft, it was about survival. If a fight turned bad, if Japanese fighters achieved superior position, Corsair pilots could simply push the nose down and accelerate away. Zero pilots who tried to follow in a high-speed dive risked structural failure. The Zero's lightweight construction, so advantageous in turning fights, became a deadly liability when speeds exceeded 350 miles per hour. Japanese pilots began reporting encounters with a new American fighter that seemed nearly invulnerable. They described aircraft that could absorb dozens of hits and continue fighting. They reported American pilots who pressed attacks even while taking fire, apparently fearless or possibly protected by some new technology. The truth was simpler and more discouraging for Japanese forces. The Corsair incorporated armor plate behind the pilot's seat, approximately 3/8-inch thick steel angled to deflect rounds from behind and below. The headrest included additional armor. Even the windscreen featured armored glass thick enough to stop rifle-caliber rounds from ahead. Total armor weight approached 240 pounds, mass that Japanese designers would consider completely unacceptable. But that armor kept Marine pilots alive. Corsair pilots could press attacks because they knew their aircraft was designed to protect them. They could absorb damage that would kill a Zero pilot instantly and still return to base. The fuel tanks incorporated self-sealing technology using multiple layers of synthetic rubber compounds that swelled when exposed to gasoline, automatically plugging bullet holes within seconds. Japanese engineers knew self-sealing fuel tanks existed, but Japan's synthetic rubber production was minimal, and by 1943, American submarines had severed most supply lines from rubber-producing territories in Southeast Asia. Japanese fighters continued flying with unprotected fuel tanks. A single tracer round could turn a zero into a fireball. Corsair fuel tanks could take multiple hits and keep functioning. The contrast in design philosophy couldn't have been starker. Japan had built elegant fighters that prioritized performance through weight reduction. Skilled pilots in lightweight, maneuverable aircraft would achieve victory through superior technique and fighting spirit. America had built a fighter that prioritized pilot survival and sustained combat capability. Adequate pilots in heavily protected, powerful aircraft would achieve victory through material superiority. In August 1943, a new Marine squadron arrived at Guadalcanal that would make the Corsair famous. Marine Fighter Squadron VMF 214, newly reformed under the command of Major Gregory Pappy Boyington, began operations with Corsairs on September 16, 1943. Boyington was already a combat veteran, having flown with the American Volunteer Group in China, where he was credited with destroying 6 Japanese aircraft. Boyington's squadron would earn the nickname Black Sheep Squadron for being composed largely of replacement pilots and misfits who didn't fit into other units. But misfit didn't mean incompetent. These were skilled pilots flying the most capable fighter in the Pacific. Between September 1943 and January 1944, when Boyington was shot down and captured, VMF 214 was credited with destroying 203 Japanese aircraft. Boyington himself accumulated 22 confirmed victories during this period, adding to his earlier 6 for a total of 28, making him one of America's leading aces. But Boyington's success and VMF 214's remarkable kill tally couldn't obscure the fact that the Black Sheep were achieving these results with aircraft that had significant limitations. The Corsair was fast and powerful, but it was still powered by an early model R-2800, producing 2,000 horsepower. Vought and Pratt & Whitney engineers knew the engine could produce more power, much more. The question was how to extract that additional performance without requiring complete engine redesigns that would disrupt production. The answer came from a technology that had been used in automobile racing for decades, but had never been implemented in aircraft on a large scale. Water injection. The principle was elegant. Inject a mixture of water and methanol into the engine's cylinders during critical high-power moments like takeoff and combat. The water absorbs tremendous heat as it converts to steam, cooling the combustion process, preventing detonation, and allowing higher manifold pressure without destroying the engine. More pressure meant more power, potentially much more power. By mid-1944, Pratt & Whitney had perfected the R-2808W, the W suffix denoting water injection capability. Installed in new F4U-1D Corsairs, beginning in April 1944, this engine could produce 2,000 horsepower continuously and up to 2,250 horsepower for brief periods with water injection activated. The performance improvement was substantial. Maximum speed increased from 417 to 425 miles per hour, but this was just the beginning. Engineers at Pratt & Whitney knew the R-2800 could deliver even more. The basic engine design was sound. The manufacturing precision was there. The cooling system could handle additional heat if properly managed. What they needed was a 2-stage supercharger to maintain high manifold pressure at altitude and enough cooling capacity to prevent detonation even under maximum power settings. The result was the R-28001-8W. Incorporating water methanol injection and a sophisticated 2-stage supercharger system. This power plant produced 2,100 horsepower continuously. With water injection activated during combat, it could deliver 2,450 horsepower. Some experimental versions achieved 2,800 horsepower, 1 horsepower per cubic inch of displacement, a benchmark considered nearly impossible just 5 years earlier. Vought installed the R-280018W in a new variant, the F4U4. The airframe required modifications to handle the additional power. An air scoop was added under the nose to provide cooling for the engine. The propeller was upgraded to a 4-blade Hamilton standard unit that could better absorb the massive torque. Unarmored wing fuel tanks were removed to improve maneuverability, though this reduced maximum range. The F4U4 began reaching Navy and Marine squadrons in early 1945. Maximum speed was now 448 miles per hour. Climb rate exceeded 4,500 feet per minute, compared to 2,900 feet per minute for earlier Corsair variants. At every performance metric that mattered, the F4U4 was dramatically superior to the aircraft that had entered service just 2 years earlier. But by early 1945, American forces had already achieved air superiority throughout most of the Pacific. Japanese aviation was collapsing under the weight of unsustainable losses, inadequate replacement pilot training, critical fuel shortages, and the destruction of aircraft production facilities by B-29 bombing raids. The Corsair and the engine that powered it had helped create that situation. Now the question was whether Japanese engineers would have any opportunity to examine these remarkable machines before the war ended. The circumstances under which Japanese engineers obtained their first intact Corsair remain documented but fragmentary. Historical records indicate that at least one F-4U crashed near the Kasumigara Naval Air Training School, apparently during American carrier raids in 1944. The aircraft was recovered relatively intact by Japanese naval personnel and transported to the Yokosuka Naval Air Technical Arsenal. Yokosuka represented the pinnacle of Japanese naval aeronautical engineering, located at the entrance to Tokyo Bay, approximately 65 kilometers south of Tokyo. The facility employed over 10,000 workers in its factories and research laboratories at peak wartime operations. The technical arsenal had designed and developed some of Japan's most important naval aircraft. Now, it would examine one of America's most formidable fighters. Japanese engineers who first saw the captured Corsair immediately recognized they were looking at something fundamentally different from their own aircraft designs. The inverted gull wing configuration was unusual but not revolutionary. What caught their attention was the sheer mass of the machine. The Corsair's empty weight exceeded 9,200 pounds. A Mitsubishi A6M0 weighed approximately 3,700 pounds empty. The American fighter was nearly 2.5 times heavier than Japan's primary carrier fighter. Where that weight went became apparent as engineers began their systematic examination. The first surprise came when they examined the wing structure. Yokosuka's specialists expected to find all metal construction throughout. Instead, they discovered that portions of the wing, particularly some control surfaces and fairings, were fabric-covered. One engineer later recalled his reaction. "We were surprised there were places on the wing covered with fabric." The observation was revealing in what it suggested about American design philosophy. Japanese engineers would have insisted on all-metal construction for a frontline fighter. The fabric-covered sections on the Corsair indicated that American engineers were willing to use simpler, lighter construction methods where structural loads permitted. It was pragmatic engineering rather than theoretical perfection. Build what worked, not what looked most advanced. But that pragmatism disappeared when structural integrity mattered. The wing's main spar was a massive forging, machined to precise tolerances. The wing center section that passed through the fuselage formed a single continuous structure of extraordinary strength. Japanese engineers calculated that this wing could probably withstand structural loads far exceeding anything their own fighters could survive. The landing gear reinforced this assessment. The main struts were robust, overbuilt by Japanese standards, but American engineers had designed them for carrier operations, repeated violent impacts as aircraft slammed onto pitching carrier decks. The gear needed to absorb tremendous shock loads and remain functional. Japanese carrier aircraft landing gear was lighter, more delicate, and frequently required maintenance after hard landings. As engineers moved to the fuselage, they found layer after layer of systems designed for survivability. Behind the pilot's seat sat steel armor plate thick enough to stop rifle-caliber machine gun rounds. Additional armor protected the pilot's head. Armored, the glass in the windscreen provided frontal protection. The total armor weight, nearly 240 pounds, was more than twice what any Japanese fighter carried. Most Japanese fighters carried no armor at all. The fuel system revealed even more sophisticated protection. Engineers cut into the fuel tanks carefully and discovered self-sealing construction using multiple layers of synthetic rubber compounds. When they deliberately punctured a section and poured gasoline through it, they watched the hole seal itself within 15 seconds as the inner rubber layer swelled in contact with fuel. It was technology Japanese engineers understood in theory but couldn't implement at scale due to critical shortages of synthetic rubber. Every system seemed designed with the assumption that the aircraft would take damage in combat. The fire suppression system could flood the engine bay with carbon dioxide. The cockpit instruments were protected by armored shrouds. Even the oxygen system for high-altitude operations was built with redundancies. Japanese designers would consider wasteful weight. Then engineers began examining the engine, and their understanding of the aircraft deepened profoundly. Removing the Pratt & Whitney R-2800 from the Corsairs cowling required several days of careful work. When they finally had the engine on a stand in their workshop, separated from the airframe, several engineers simply stood looking at it. They had seen intelligence reports describing the R-2800's specifications. Reading numbers on paper and confronting the physical reality of the engine were entirely different experiences. The R-2800 weighed approximately 2,360 pounds, more than half the empty weight of an entire Zero fighter. 18 cylinders arranged in 2 rows. Each cylinder displaced over 155 cubic inches. Total displacement was 2,804 cubic inches, 46 litres. For comparison, the Nakajima Sakai engine powering the Zero displaced 27.9 litres and produced roughly 1,130 horsepower. Engineers began systematic disassembly, photographing every step, measuring every component, taking detailed notes on assembly techniques. The R-2800's internals revealed manufacturing precision that Japanese factories struggled to achieve consistently. The crankshaft was a massive forging, machined to tolerances measured in thousandths of an inch. Connecting rods showed evidence of advanced metallurgy and heat treatment processes. Cylinder walls were precisely honed to dimensions that varied less than 2/10,000ths of an inch across multiple cylinders. Every component appeared designed not just to function, but to function reliably under sustained high-power operation. Bearing surfaces were oversized compared to Japanese practice. Oil passages were generous. Cooling passages through the cylinder heads were carefully designed to prevent hotspots. The engine had been engineered with substantial safety margins, built to produce 2,000 horsepower not as a maximum emergency setting, but as sustainable combat power. The supercharger system particularly impressed the power plant specialists. The R-2800 employed a sophisticated 2-stage, 2-speed supercharger that could maintain high manifold pressure across a wide altitude range. Japanese engines typically used simpler supercharger designs, a compromise driven partly by manufacturing limitations and partly by emphasis on low-altitude performance where most Pacific combat occurred. But the American supercharger represented precision manufacturing that required machinery and quality control processes Japanese industry couldn't consistently provide. The impeller had to spin at tens of thousands of revolutions per minute, while maintaining precise clearances with the housing. Any imbalance would cause catastrophic failure. Any degradation in clearances would reduce efficiency. Dramatically, American engineers had solved these problems. Japanese engineers understood the solutions in theory, but lacked the industrial infrastructure to implement them reliably at scale. The fuel injection system revealed another critical advantage. While Japanese engines still predominantly used carburetors that could cause fuel starvation during negative G maneuvers, the R-2800 employed sophisticated injection that delivered consistent fuel flow, regardless of aircraft attitude. This seemingly minor detail had profound combat implications. American pilots could push over into negative G dives without their engines cutting out. Zero pilots had to roll inverted before diving to maintain positive G and keep their engines running. That half-second of extra maneuvering could mean the difference between life and death. As examination continued through late 1944 and into 1945, engineers documented everything in comprehensive technical reports. But the captured Corsair they were examining was powered by an earlier R-2800 engine producing 2,000 horsepower. Intelligence reports reaching Japan indicated that newer Corsair variants were appearing in combat with even more powerful engines. The F-4U-4, now equipping American squadrons, reportedly achieved speeds approaching 450 miles per hour. Japanese test pilots who evaluated the captured Corsair confirmed what combat reports had been indicating for months. The aircraft's performance overwhelmed Japanese fighters in every metric except slow speed turning radius. The Corsair could climb faster, dive faster, accelerate faster, and maintain higher speeds than any Japanese fighter in service, and the massive R-2800 engine made it all possible. One test pilot's report captured the essential problem facing Japanese aviation. American pilots can choose when to fight and when to disengage. We cannot pursue them when they dive away. We cannot climb with them when they zoom upward. We must wait and hope they make mistakes. But they are making fewer mistakes, and we are running out of pilots. The brutal mathematics of attrition were becoming inescapable by early 1945. American aircraft production had reached 96,000 aircraft in 1944. Japan managed approximately 28,000. But those numbers understated the real disparity. American aircraft consisted of thousands of precision-manufactured interchangeable components. They could be maintained by mechanics with basic training using standardized replacement parts. They could be repaired in the field quickly and returned to service. Japanese aircraft remained largely craftsman-built machines, requiring skilled technicians for maintenance. Each aircraft was slightly different, requiring custom fitting of replacement components. Field maintenance demanded highly trained mechanics who understood how to adjust and modify parts. As Japan's pool of skilled workers shrank through combat losses, industrial accidents, and bombing casualties, maintaining aircraft in service became increasingly difficult. The Corsair exemplified everything Japanese industry couldn't match. The aircraft was designed from the beginning for mass production by workers who didn't need years of specialized training. Dies and precision tooling built quality into the manufacturing process rather than relying on craftsman skill. Components were machined to tolerances that ensured interchangeability. Any properly manufactured part would fit any aircraft of the same model without adjustment. The R-2800 engine represented the same systematic approach to manufacturing. Pratt & Whitney had designed the engine knowing it would be produced by multiple manufacturers, including Ford Motor Company's massive River Rouge plant. The engine had to be buildable by automobile workers using automotive manufacturing techniques. Every dimension was precisely specified. Every tolerance was carefully controlled. Quality couldn't depend on individual craftsman judgment because there wouldn't be enough trained craftsmen to build engines in the quantities required. By 1944, Pratt & Whitney and its licensees were producing R-2800 engines at rates Japanese engineers found difficult to believe when they calculated the numbers. The engine powered not just Corsairs but also Republic P-47 Thunderbolts, Grumman F-6F Hellcats, Northrop P-61 Black Widows, Douglas A-26 Invaders, Martin B-26 Marauders, and numerous transport aircraft. Total R-2800 production would exceed 125,000 engines by the time production ended in 1960. Japanese engineers examining the captured Corsair in early 1945 understood they were looking at more than just a superior aircraft. They were confronting evidence of an industrial system that Japan couldn't replicate even if given years to try. The Corsair wasn't superior because American engineers were more clever or Japanese engineers were less capable. The Corsair was superior because American industry could build it, in quantity, to consistent quality standards, using a workforce that didn't require years of specialized training. The engine specifications told the same story. The R-2800 produced 2,000 to 2,800 horsepower, depending on variant, using manufacturing processes and quality control systems that Japanese industry couldn't consistently achieve. More powerful engines existed on Japanese drawing boards. The Nakajima Homare, the Mitsubishi Corsairs, various other designs promised impressive performance, but promises on paper meant nothing if the engines couldn't be manufactured reliably or maintained in service. Japan had entered a war of industrial attrition against an opponent with 10 to 20 times its manufacturing capacity. Capturing and analyzing enemy equipment revealed the problem clearly, but provided no solutions. Understanding why you're losing doesn't change the outcome when the gap is insurmountable. By spring 1945, the strategic situation had become hopeless. American forces were approaching Okinawa, bringing the war to Japan's doorstep. B-29 superfortresses, powered by R-3000, 350 engines that represented the next generation beyond the R-2800, appeared over Japanese cities in formations that defenses couldn't stop. Each raid destroyed production capacity that couldn't be replaced. The Nakajima plant at Musashino, Mitsubishi facilities at Nagoya, Kawasaki factories, all suffered severe damage from precision bombing. An earthquake in January 1945 compounded the damage to Mitsubishi's supplier network. Japanese aircraft production collapsed. Monthly output fell from over 2,500 airframes in May 1944 to barely 1,500 by early 1945. The decline continued through the war's final months. The captured Corsair at Yokosuka had taught Japanese engineers that their defeat was inevitable. Not because Japanese pilots lacked courage or skill, not because Japanese engineers couldn't design competitive aircraft. The defeat was inevitable because modern industrial warfare was won by production systems, not by individual craftsmanship. The nation that could build adequate aircraft in overwhelming numbers would defeat the nation that built superior aircraft in inadequate numbers. And when both nations could build excellent aircraft, the one with greater industrial capacity would simply outlast the other through sheer attrition. For every Corsair shot down, American factories produced 3 replacements. For every R-2800 engine destroyed, Pratt & Whitney built 4 more. Japan couldn't match that output, couldn't come close. The mathematical certainty of defeat had been visible in the Corsairs' construction methods, in the R-2800's manufacturing tolerances, in every precisely machined component and perfectly formed panel. After Japan's surrender in August 1945, American technical intelligence teams occupied Yokosuka Naval Air Technical Arsenal. They found the captured Corsair, still bearing its American markings beneath Japanese inspection tags and documentation. The aircraft sat among dozens of other captured and indigenous Japanese aircraft, all tagged with meticulous Japanese technical notes. American engineers were struck by the thoroughness of the Japanese analysis. The examination had been professional, comprehensive, honest in its assessments. But honesty in assessment couldn't bridge the industrial gap. The captured Corsair had revealed truths that no amount of Japanese determination could change. In the decades following the war, those lessons would reshape Japanese industry completely. Engineers who had examined American aircraft during wartime brought their understanding of American production methods to Japan's reconstruction. They recognized that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation required 20 years. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and systematic processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing that had been organized as collections of skilled workers evolved into integrated production systems. By the mid-1960s, Japanese factories were producing automobiles and electronics using methods comparable to American mass production. By the 1970s, Japanese manufacturers had refined those methods, developing production systems like Toyota's just-in-time manufacturing that improved on American techniques. The precision that had once come from craftsman's skill now came from precision tooling and equipment. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out, and don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.